is recording. Okay. This is not you. This is you. Your questions on this exit ticket. It says, what are the applications, the counting in computer science? So there are many applications. So one of them, I could say, if you're supposed to design a network, so one person is administration, and then you have many other computers that you need to connect them. So those are one of the possible ways that you can just minimize the wiring. You minimize just the system as you're just getting connected. All of the system maybe in your computer science. Anyone else has any example for application of counting in computer science? Possible. I think for writing the programs, when you're just writing any loop, and you need to know how many times your loop is supposed to back and repeat those loops. That's just one of the counting problems that you're really required to know, and you want to always have those many loops to be minimum because you don't want to get longer, right, programs. What else we can say about counting on the program side, programs or computer science? These are the things that I have in my mind, but I know there are really many. There are many of those. Oh, that's the same.
It may not even be computer science specific. It might just be, I have to write software for this problem specific, and I have to understand. That's how I think about it.
But directly permutation computations is counting in your computer science programming, and you're applying those rules. Oh, I know. This is really something that we try to make it in the first exam. The first question says, there were, if I just go back on the table that is posted online, where was it? Right over here, you see. If you say permutation, so you're really ordering things. So when you say permutations, you're ordering things, and that is just with the repetition or not repetition. But if you do the combinations, the order doesn't matter. You're just really selecting. It doesn't matter which order you're putting. So like just if you're writing a word, it's just permutation because the order is changing different word. So or the numbers. If you reorder it, you're creating a new number. But if it's just really selecting like just pants or shirts, the order really doesn't matter, okay? So those are called combinations. And then permutations, as we said, is the one that we have the order. And then for those stars and bars, as you see in this table, is really clear. It's the kind of selection or combination problems, the selection or combination problems that you have repetition. So those stars and bars is coming when you have repetition because they are same identical items that you want to select them, not order them. So you just select them. So for the cookies and kids, always good. They are good examples because cookies are all identicals, kids are all identical, sorry. So then when you're just maybe cookie number 4 has no significant things that is different than cookie number 5. So the order doesn't matter. It's really all of those cookies that you want to just distribute between the kids. So again, combinations with the repetition is that stars, bars problems. But I know that's just really the main challenging because there are 4 different types of problem. I have to decide which one is which one. This is a good comment. Which we just, number 2, I explained right now.
Yeah, sure.
Yeah, that's the same. Yeah. Thank you so much. Thank you so much for your comments. I have only Jan left here. Okay. As I said, actually I've done my section of recursive equation, except one example, if you remember, we skipped it in the previous class. And then that was a telescopian method. That was this one, right? So the telescopian method, and I have a few more examples. I think I have 4 examples to make this one clear. What is the telescopian? And we have iterated method. And then we have that easy one, I'll call it easy version. The one that we have as quadratic equation, this is a good one. I can just easily take care of that. But then if you have the other method, I think we haven't tried any example. I'll try and you'll see it makes sense. Sometimes if you do in that way, it makes sense. For equations that looks like, just again, equations that looks, you have recursive rules, or that means your term, your nth term depends on the other 2 terms. That's just because one term depends on 2 other terms, it's making quadratic equation, so which is fine, okay? So again, you write corresponding characteristic equation, you get your x's, and you know what's the form of the solution. You form it in this way. If it's repeated, you add another n, okay? So this, I'll practice those problems too, okay? But for now, let's say this is not a 2nd degree recursive equation. It's only 1st degree recursive equation, like this one. We'll try 2 different methods. One of them is called telescopian, the other one is called iterated method. When we write them, you know, if you pass your calculus too, you know what does it mean when we say telescopian. If you didn't pass, you need to see it over here, okay? Telescopian one in calculus 2, it was the one that everything canceled out, only 1st term and last term left in series, if you remember. But it's, if you haven't passed it or you don't remember, that's okay, because I'm doing here. So I have 2 different methods for one recursive equation, which is a 1st degree equation. It's a 1st degree equation. What does it mean? That means your nth term depends on the only 1 term before that, not 2 terms, which is the 2nd degree, or we have easier method for doing that. So if I want to go by iterated form, so let's see, your first term is your initial term plus whichever n is. Your 2nd term is your previous term plus whichever n is. So if you replace your 1st term from the above equation, so you have this, and then you have plus 2. Your 3rd term is your previous term and plus whichever n was 3 in this time. So if I replace for that one from the previous, it was a0 plus 1, and then plus 2, and then you have a plus 3. And then if you have a 4th term, do you see, seems is following some rules, right? So if I'm doing all the way, like just saying a few more, sorry, the previous term, and then plus the n. So I replace that a sub 3 from the above line. So 1, 2, and then 3. And then you're adding 1, 4. So tell me what's happening if I keep going on nth term, which is going to be 1 term before plus n. What should I have? I write it in orange. So a sub 0, initial 1, 2, 3, all the way to n minus 1. Okay, and that's the orange one. You are right, it's ending with the n at the end, right? Because I'm adding that n, which is for the a sub n, okay? So the initial term actually is given is 4. So your a sub n equals your initial term, which is 4, and then addition of these 2 numbers. Addition of these 2 numbers. Do I know what's the addition of this sequence? Do you know what's the addition of 1 plus 2, 1 plus n with arithmetic sequence formula? That's the arithmetic sequence, is it? 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, right? So this is the arithmetic sequence. Do I know what's the sum formula for arithmetic sequence? What's the sum formula for arithmetic sequence? N half first term plus last term. Okay, n half first term plus last term. So that's the formula for arithmetic. Even if you don't know what's the arithmetic formula, that was just something that we tried it in our, what was it? Binomial theorem to prove it. In binomial theorem, we proved that addition of the numbers equals n times n plus 1. Even it was in your first test as the problem on induction. No? So we tried that one. So, but still is easier because we are in the section of sequences. Look at it as a sequence. Is the arithmetic sequence and follow this S or some formula for sequence. So this is it. If n is 1, what do you mean?
Because you said it's you had the first semester. If it's 1, you do 1 plus 1.
Oh, that's a good question. Let's just go back over here. So you're having S sub 1. So let's say S sub n was n divided by 2, first term plus last term. I'm going to check what do I have. You're having 1/2 and then 1 plus 1. So that's true. If you make it S sub 1, you have to, yeah, that's true. That is really interesting question. That was really interesting. So if you have S sub 2, basically it's supposed to be 1 plus 2, right? So that is 2 terms divided by 2, first term plus last term. So that's why it's 3, and that makes sense. That was a good question. Okay. This is what we call solution or what we call closed formula. So closed formula or solution for that recursive equation with this iterated form, with this iterated method, okay? And then I have another method which is called telescopian. Typically, telescopian should be easier problem. Again, if you pass your calculus 2, you remember telescopian sequences was the easy one. Typically should be the easy one. Do I have any question before moving to the second method? Yes, no, move on. So then I have to, for telescopian, the terms cancel out. 2 by 2, the terms cancel out. You have left with the first term and last term, okay? So let's say your initial term was 4. Your initial term is 4. Your first term is initial term plus 4. So then you can write it first term minus initial term equals 4. You just rewrite it in the negative sign because you need your negative sign to cancel them out. So then your second term is going to be first term plus, did I write something wrong? Plus 1, sorry. That was n. Yeah. It's always previous term plus n, which is 2 here. So then your subtraction of these consecutive terms is 2. And then if you have a sub 3 is a sub 3 plus 3. So then subtraction of a sub 3 minus a sub 2 is 3. Is that okay? This is fine. How many terms did I write? I just wrote by 4th. So that is previous term plus n. So then a sub 4 minus a sub 3 is 4. Okay. Then if I keep going on n many, so you're having the rule or just the recursive equation, which is the previous term plus n. So then subtraction minus the previous term equals n. Okay. Do you see in this case, which is called telescopian one, it has to be really that 1 plus minus. It has to have this nice form. If you start to add both sides of the equation, actually there are many n equations. So on the left side, you're having 1 plus a sub 1, 1 minus, they cancel out. You're having 1 a sub 2 minus cancel out. You're having 1 positive, 1 negative cancel out. Probably next line, this cancel out. So all of those negatives cancel out. Does it make sense? if you add the left sides of the equation, the rule of telescopian is typically you stay with the first and the last one. So you are making a positive, negative, and then you just add both sides of the equation. So you have left with the very first term, typically, and the last term. Sometimes we have one more term, okay, depends on the problem. So then your left side, as I said, last term and first term left. The right side, if you add all, is going to be 1 plus 2 plus 3 all the way to the n, which again is arithmetic sequence. That is that some equation, that some formula for the arithmetic sequence was n half first term plus last term. And that's exactly the same solution that we got once. That's exactly the same solution with different method, okay? Any question here? Any question here? I have one more example on the iterated one, but before just comparing with the iterated one, oh, sorry. Sure. Before completing that example on the iterated one, I just want to remind you, if you have a second degree recursive equation, forget about iterated and telescopian. You can still do that easy method, which is solving characteristic equation, okay? I don't know which one I tried in last class. Let me check. I have 7 and negative 10. I have 6 and minus 9. And I have this one, which we haven't tried it. Okay, so I'll try this one. So one more example, just to tell you, there are 3 different methods to do this type of problem, okay? If you're getting the recursive equation in terms of 2 terms, or what we call second degree recursive equation, you need to make it everything to the left side, write it as quadratic equation, which we call it characteristic polynomial, and then you can just get the solution by the formula. So those iterated formula or those recursive equation is not for this type of second degree equation. Does it make sense? Agree? So I moved everything to the left side. I have an minus 3an minus 1 minus 4an minus 2 equals 0. So this is x squared minus 3x minus 4 equals 0, which is the characteristic formula or equation corresponding by this equation. This is factorable. If not, you can go by quadratic formula. The negative 4 plus 1 works, right? So then your solution was a 4 and was a negative 1. So rule, according to the formula in previous class, says your closed formula or solution is going to be a constant 4 to the power of n, another constant negative 1 to the power of n. And those initial values is for getting those constants of a and b. It's a little bit algebra that we need to plug in n equals 0 and n equal 1 and take care of that solutions, okay? Does it make sense? So this type of the recursive equation has nothing to do with iterated or telescoping one, okay? So if you set n to be 0, your a sub 0 equals a times 4 to the power of 0 plus b times negative 1 to the power of 0, which is given to be 2. And then if you plug in n equals 1, your a sub 1 equals a 4 raised to the power of 1 plus b negative 1 raised to the power of 1. So that's given to be 3. A sub 1 is 3, so it's a minus, 4a minus b. And then, as I said, it's just algebra. You need to take care of your 2 variables, 2 equations, and then find the a and b. I think it's easy one, right? Why easy one? Because that has the negative. So then easily your solution was a equals 1, 4 to the power of n. B also equals 1, negative 1 to the power of n. So that's your last solution. Okay. Question on this type of problem? Any question on this type of problem? The second degree recursive equation? Does it make sense? I have one example that is, again, first degree. And then your initial is 5. This is first degree and your initial is 5. This is with the iterated method. Try to write down whether you see the rule. Try to write down the A sub 1, A sub 2, A sub 3, and see whether you see the rule that somehow you need to use sequences. Somehow you need to use sequences. So can you please write down your terms like A sub 1 equals A sub 0 plus 2 to the power of 0. Oh, sorry, 2 to the power of 1. A sub 2 equals A sub 1 plus 2 to the power of second. A sub 3 is A sub 2 to the power of third. A sub 4 is A sub 3 2 to the power of 4. Anything related to the sequences? Anyone has the rule? Anyone could see the sequences? No? No one yet? It's really similar to mine, right? The one that I tried at the beginning. You're looking for, I think if you keep them as a power, it makes more sense. Right? So you have 2, then the power of second, the power of third. And it's kind of sequence do you have, right? Kind of sequence do I have? The reason that's called iterated because it's a repeating back to back. So, not yet. Yeah, it is recursive. Whichever things is back to the previous term is called recursive because it's
Right.
recurrent. But it's very simple. So this is just perfect, right? So this seems it's just really going by to the verbs in a second, third, fourth, and so on. So that's corresponding to the geometric sequence. So I think that is repeated in the geometric sequence. No? Do you see the geometric sequence? No? If you didn't learn it, you also do a sub one is this, a sub two is this. Keep this back what you have. So if you don't replace back, has nothing to do with the iterated. When we say iterated means you replace back. So what I mean, your a sub 1 is a sub 0 plus 2 to the power of 1, and then you're having 2 to the power of second after. And then your a sub 2 is a sub 0, 2 to the power of 1, 2 to the power of second, second. And then your next term is 2 to the power of 3. And then that's the meaning of iterated, because you back and then replace the whichever you got from the previous term. And then your a sub 0, 2 to the power of 1, 2 to the power of second, and 2 to the power of 3. And then your last one is 2 to the power of 4. So as we see, if you go to the nth one, and then you repeat the previous term plus 2 to the power of n, so you must have the all power of the 2 by n minus 1, and then your next term is 2 to the power of n. So it's very similar to mine. Your an, and then your a sub 0 given to be 5, and then you have a sequence here. What's that sequence?
You end up using the same formula, so was it n divided by 2?
No, that's just for arithmetic. You have to use the geometric version of that.
I'm thinking about the,
You have to use this formula because yours is geometric formula, geometric sequence. It's not adding terms. So it's 2 to the power of 1 times 2 times 2 times 2. So that's why you have to use the geometric sum, not this arithmetic. I use the arithmetic one, this one, because mine was adding terms, adding common difference to get the next term.
so I understand that. What I'm saying is the 2, you can put that arithmetic sequence in the exponent of the 2 is what I'm asking, because you have 2, 1 times 2 is 2.
It's not times, it's plus. If it's times, you're right.
Oh, it's plus.
I see what you,
Oh, okay.
they are plus.
Okay,
If
I
it
got
was,
it wrong.
yeah. So then you were right, exactly. So then what's the formula for the sum of geometric sequence? This is a geometric sequence with the r equals 2, so that was a 2, and then, initial term, 1 minus the common ratio to the power of n plus 1 divided by 1 minus common ratio. Okay. I have a negative sign here, huh? I have a negative sign on the numerator. I have a negative sign on the numerator. So it's a negative 2 plus 2 to the power of, am I right? I distributed this one inside, right? So I have a negative 2 and then plus, and then this is 2n plus 2. Can I check my formula? Sorry. I think yours does n minus 1. Can I check quickly the formula? I think it's r to the power of n minus 1. Where is it? Oh no, it's n. So initial term 1 minus r n, 1 minus r.
There's no subscript.
So you're adding n terms, right? So your initial term is 2 to the power of 1. And then your, yeah. Initial, I'm talking about this sequence, sorry, not that initial term. Sorry. I'm talking about that sequence that I'll call it B. That's not for any confusion. I call it B, sorry, that's better. Thank you. So if I call it the initial term is B sub 0, I talked about this power. So that's why I'm repeating, okay? I'm thinking about that power. So according to the formula, if I'm adding n terms, it has to be initial term and then 1 minus r to the power of n divided by 1 minus r, okay? So my initial term is b to the 2 to the power of 1, and then my n minus 1 term is 2 to the power of n. Do you agree with me? 0 gives you 1. N minus 1 gives you 1 more, which is n. Yes? So that many terms I have is really r to the power of n, not n plus 1. Agree or no? Yes? Are you okay with my subscript? I'm adding n minus 1 terms. Oh, sorry, I'm adding total of n terms, starting from the 0. Starting from the 0, there are n terms. You're adding exactly n terms. So that's why that power is n, starting from the 0. Okay?
So I'm confused. I thought A0 was 5. Is it? Am I reading that
Yes. A sub 0 is 5. So I replace A sub 0 equals 5. And then I'm looking to, I called it B. I'm looking the whole addition of the twos to replace it by geometric sequence. Huh? So that's why I changed the name to be like B sub 0.
right? Okay, I think it's.
Okay. Enough examples? Can we move on of this type? Can I move on this type? This is, yes, I have to move on. It's for 40 minutes of this. Okay. As I said, the new topic, I don't think you guys have any problem with this new topic. Even if you have never seen it in your life, it makes a lot of sense as far as the application. Again, if you are programming, or just maybe designing any kind of networks, so you are actually doing all of this fun stuff. Have you ever seen graph theory? Graphs? So it has the list of definitions which we need to practice and remember. And unfortunately, for some books, they have different ones. So sometimes even I'm confused about which called here to be path. Sometimes in other, between the cycle and closed path. So there are different terminologies. And it's not unique for all of the entire books that we have in graph theory. So we are just I'm trying to follow exactly whichever definition is in your book. Otherwise, sometimes it's a little bit different between what we call closed path, or what we call cycle, and what's the other kind of definitions, okay? So basically, when we say graph theory, it's just really the rules that we can have between a bunch of dots and lines, the lines. So you have many dots and you just have a line that connect those dots. So that's what we call a graph, okay? We have different types of graph. We are talking about simple graphs, so which I'm going to explain what is a simple graph. So we don't want to get any intersection between edges, okay? So think about if you are just really designing a network, so you don't want to have any connection between any administration that you're defining from your headquarters, okay? So then I'll say there are 3 properties to call something to be simple graph, okay? So it's soon, so just wait for me, it's coming. First of all, the formal way of defining what we call a graph, as I said, a bunch of dots, which we call it vertices, and a bunch of lines that we call edges. Do I have always connection between all of these? No, they could be really separate one. They could have some connection. Maybe there are some dot right over here without any edges, which is fine, okay? So if I want to say formal definition, as I said, for now, I'm talking about simple graphs, and I'm just going to explain what is the simple graph. The simple graph consists of a non-empty set of V stand for vertices, and which is the bunch of dots, or what we call nodes or vertices. They are the same. And a set of edges. So the set of edges, E stand for edges, and there are always 2 elements. So you need 2 dots to make 1 edge. So it's 2 elements subset of your vertices, And then if you want to just write it with the notation, your G stand for the graph. You have disordered page. The first one is set of all your vertices. The second one is the set of all edges, or the lines that you have between 2 dots in your graph, okay? So that's the terminology. Does it make sense by now? So if I check this graph right over here, if I check this graph, the original one without any changes right over here, my set of vertices are V, as you see, A, B, C, D, E, F, G, I, and H. So that's the set of all vertices you have. Notation wise, if I want to show the edges, I have to use exactly a subset of 2 elements. So the subset that has 2 elements. So when we say AB, that's the set of edges, okay? So AB is 1 edge, AC is another edge, BD is another one, where is it? BD is another one, CD is another one, and then CE is another one, and then EF is another one, and EG is another one, and HI is another one. Okay, so that's the set of E stand for edges, the possible edges that you have in this graph, okay? Fine? Yes. By order, no, that's a set theory. Set theory, the order doesn't matter. If you reorder it, it's fine. So it's just really listing all of them. Repetition does not make sense, right? So it's set theory. As we know, if you have a set of A and A is the same as set of A. So repetition doesn't matter in the set theory. If you have A and B is the same as B and A. The order doesn't matter in set theory. That's exactly set, so no. So the other terminology I have, if you're having 2 vertices, in any simple graph that has 1 edges, okay, so it has 1 edges, is called adjacent. So if you have 1 edge connected 2 vertices, is called adjacent vertices. And then we have the edge to be incident. If you're having 2 dots connected with that edge. So edge is incident. if the vertices that joins that what was it, dots or vertices, okay? So the number of edges incident to a vertex is called the degree of that vertex. So let's go back on top. So if I start with the D, the number of edges that incident is called the degree of the D. So D has degree of 2. If I start with the E, the number of incident edges, which is 1, 2, and 3, from the E connected to the what we call adjacent dots or adjacent vertices is 3 of them. So the degree of E is 3. Does it make sense? So one more time, it says over here, the degree of any vertex simply is exactly the number of your adjacent vertices. Is the number of adjacent vertices, okay? First one, can we find 2 adjacent vertices in this graph? 2 adjacent vertices in this graph? 2 adjacent vertices, like there are many of those, right? So you can say E and G. E and G is adjacent. Maybe E and F is adjacent, okay? So maybe H and I is adjacent. There are many, right? Okay. So, sorry, I'm sorry. So what is the degree of the vertex H? What is the degree vertex H? Only one, right? It has only one adjacent or incident edge, okay? So what is the degree of D? I think we just take care of the D, right? So as an example, it was 2, right? There are 2 adjacent dots, or there are 2 incident edges, okay? And then E?
You can just look at this set. You don't even have to look at the graph.
Yeah, either one, yeah, that's fine. So there are 3 of them. Question? Comment? Special cases? No? Think about. So this is the place that I was going to explain what is the simple graph, what we don't like to see in this simple graph or this chapter, which is possible in real world. With the real world problems, you might see all of these kind of cases, which is not the rules that we are learning is only for simple graph. So number 1, it says, when we have a simple graph, there is no self loop. So what is the self loop? So if you have a vertex A and vertex B, so that's one edge, and probably this is another edge. We don't see this kind of self loop. So A back to the A, we do not see in the simple graph. So that's number 1, we don't like to see in, or we won't see in the rules that we follow in this chapter. Then if you're, so then the second one, at any 2 sets or any 2 vertices that you choose, you should say only one, at most only one edge. So if you choose any A and B, A and B, either there is no edge or is only one edge. You can't see this kind of the graph. This is not a simple one. So this is not a simple. So it says at most you can have one edge. So either no edge or you just have one edge. So we don't like to see what we call multiple edges. So what we call multiple edges, it's not a simple graph, okay? It's not a simple graph, which is possible. Really in real world problems is fine. It's possible to have. And the most importantly, we don't have any directed edges here. So directed edges means if you start from the A to the B, if you start from A to the B, this arrow like this, we've seen it in one homework, only one example of the homework, you had that arrows, we don't want that. So that's not the directed graph. So this is not the directed graph. So those three, I will say, criteria for just making sure we are having a simple graph. Okay, making sure we are having a simple graph. Okay, and there are many special cases. Okay, so there are many special names, I will say, for my graphs. I'm having only one of them over here, and then later I list the rest of them. Okay, so first of all, the first one, or the simple one, is called complete graph. So what is the complete graph? So the notation wise complete graph is K, and then the subscript shows exactly the number of vertices. So if you say K sub n, you have exactly n many vertices. And then it says it's called complete graph if you're having one edge between every two vertices. So let's just try. Let's say you're start with the 3 dots. So I'm writing my K sub 3 for now. Okay. So if you're try A, B, and C, it says an edge between two vertices. So this is one, this is one, this is one. Okay. Can I make any other lines? So then your K sub 4. A, B, C, and then D. Which one is left? Which is not connected? Can I connect C to the P? I can't cross it, but I can go this way. Okay. Yes, I need to connect them, but that's not just crossing, because actually, is it any wrong to cross it?
Yeah, I think I thought on the above graph, I thought it implied that they could cross, and it doesn't mean that.
I'm thinking about being simple, because in being simple, it didn't say doesn't cross it. No, no, we can have the cross.
Yeah, scroll to the next one.
To the previous
Yeah,
graph.
yeah, to the last. Yeah, because there's a cross right
Yeah,
there.
it crosses.
Yeah. And again, as I said, it's not listed over here as the criterias. It's okay to cross. It's okay to cross, okay?
I think as long as all of the vertexes are explicit, you're not gonna be like, oh, well, you didn't count this cross.
You know, once I was thinking about my calculus 3 class, and then when we are doing the double integration and we don't have a simple surface over there, their simple surface means don't cross, but here it's okay, sorry, you're right, it's okay, you can cross it. So then either one, you know, you can just really just make, I mean, a case of 4 should not have exactly this way. So if you have another A, B, and then like equality or equivalency, if you have this one, this is as far as the network, as far as the graph, these two are equivalence. These two are equivalent. You will see the functions between these graphs, okay? But that's just really equivalence function, I mean, graphs. So they are equal graphs. So one more time, you're connecting A to the B. We have with the 5 dots, okay? Here, here, here. So that's for all of the A's. Here, this is for C's, right? So 1 and then C, it has all of them. For the D, I have this, and then I have to have this one, and then I have to have this one. For the B, I have to the A, I have not to the E, and then I have to the D, and then I have it to the C. I have all of them. Is that fine? Do I have all of them? Huh? Okay, so then I'm going to make a rule for, again, as a sequence. I'm just looking as a sequence. So if you're having a graph, which is just as you tried K sub 3, K sub 4, and then K sub 5, and probably you can continue to the K sub n, okay? So you can continue to the k sub n. But I'm looking for exactly the number of edges. Okay. Is it always -1? So how many edges for k sub 3? And then how many edges for k sub 4? 6. How many edges for k sub 5? Any rule? Any relation? Then we can guess for k sub n. I'm looking as a sequence, huh? Why 6? 1, 2, 3, 4 sides, and 1 diagonal, 5, and then the other diagonal 6. Can you tell me which one you didn't count it?
Oh, no, because I thought you said edges. So I was thinking like, the dots, not the lines.
Oh no, the edges are the lines. Okay.
We need a notation for factorial addition.
Factorial addition. They use sigma, they are happy about that.
What's that?
Addition, they use the sigma, but they just say sigma n.
Oh, yeah.
They're happy about that. So this is one guess or one sequence that's going on for this. When you're writing n, is exactly 1 plus 2 plus 3 all the way to the n. Or n minus 1, you're right, n minus 1, one less is n minus 1, which is one less. So that's why that rule is just, again, arithmetic sequence. So the number of edges has a formula. It's always n times n minus 1 divided by 2. So you can always find for n many vertices. If you want to connect all of these vertices, you have to find n times n minus 1 divided by 2, what we call edges, huh? Can you just give me the formula for counting? You have n vertices. Can you give me one combination formula for this number of edges?
See that number of edges is to 1 to 1 vector times equal to 1 to 1 plus 4. So if you set them to be n times if you set the 10 to be n times 2.
Almost. I see what you're thinking about. Okay. One more time. So you're making edges, right? So for edges, you need 2 dots. So how many selection of 2 dots out of total many n? This is the same as n choose 2. This formula is the same, n choose 2, because you're supposed to choose 2 dots to make one edge, and then you have n many of those. So it's really the same as selection of 2 out of n. Does it make sense? To make the edges. It gives you the same formula, okay? It gives you the same formula. Yusuf, you have something to add? You're thinking about something.
Is this a handshake problem? You have so many people in a room and each one has to shake each other.
Yeah. That's the same. No, that's the same. Exactly the same answer for that one, because there are selection of 2 out of n many people. Yeah. What was yours?
No, I'm trying to remember it because I took the graph during the whole.
Oh yeah. So what's the empty? Can I move on? what's the empty graph? So again, there are just two of them here, and I have much more than that. So the other name is empty graph. So empty graph has no edges. Empty graph has no edges. So A, B, C, probably D. Okay, empty graph has no edges. So actually it says make it with the 5. So I need one more, maybe C, D, E, because it says make the empty graph with 5 nodes. Oops, I did something. How do I undo? Okay.
I'm kind of imagining the step of it, like would it be V equals set of A, B, C, D, E, and then E equals empty set?
That's true, right? So V equals set of A, B, C, D, E, and E is empty set. Okay. And another type is a line, the L sub n. So it's just the line graph. It is a line graph with n vertices. It is a line graph with n vertices. And it makes sense, you see. So you're having, let's say, V sub 1 and then V sub 2 that's connected. So then V sub 2, maybe V sub 3 that's connected. V sub 3 and then V sub 4 that's connected. Do you see? The subscripts are 1, 2, and then 2, 3, and then n minus 1 n. So it follows. That's just really what we call the line. So it's all about the number of vertices, which is n many, and then you connect them, okay, linearly. You can't back to the same. Go ahead.
For the empty graph, E is not 0, right? Like for that.
It's empty, not 0. It's empty, not 0. Empty. Yeah, because we are just really having two different concepts, right? So when we say empty is about set theory, has no elements inside. When we say about real numbers, when you're counting, so you just say, I'm counting, I don't see any edges, so it has 0 edges, okay? So it's set theory and numbers.
Cardinality, is that ever used in notation for this? So like what he's talking about, where it would be 0 if you're counting them, but are you ever going to show us like the bars?
Cardinal, so you mean cardinality of this is 0?
Yeah, or B.
Yeah, or
Well,
cardinality
yeah,
of V is
kinda
5.
obvious, yeah.
Yeah.
Okay.
Yeah, it's about number or sets.
Yeah, I had that question.
Okay. And any other question? So here it says make it with the 5 L sub 5 or 5 edges. So I'll start with the V sub 1, V sub 2, V sub 3, V sub 4. It's just, I'm making to be down or up just to tell you it doesn't have to be really straight line. It could be just maybe like this, still is called the line. Okay, so this one is still called line graph. Okay, and then what happened if you're connecting the first and the last? What happened if you're collecting first and the last? Let's say you start with the first one. That's kind of, huh?
Yeah, not a circle, I guess, but it repeats. It's continuous.
We call them cycle, which makes sense, right? So we call them cycle graph, or maybe cyclic graph, okay, which is the same. So line, so as of now, we have learned about the complete graph, empty graph, line graph, and then cycle graph, okay?
Like a linked list. A circular linked list.
I left one C, huh? Thank you. And weighted graph, it makes much more sense for you guys, right? So think about any of those possible networks or just fibers that you're trying to make. So let's see what are the examples. I like to read the examples because this is really when your number of your edges has some weight, okay? Easy example will be your highways. So if you're moving, let's say from San Diego to the Los Angeles, there are 5. I think there is another one, 73. So there are a few highways, okay? So those paths, each one has a weight, which could be really the maybe speed, capacity, just I don't know, whichever criteria you might think about any highways might have. Okay, so then you can assign numbers to that and think about, okay, do I choose 5 to go up, or do I choose another highway to go out? So that's one of the things you can think. So I'm going to read the examples because that much more sense when we go. Let's say you're supposed to have the internet fiber and with any pair of computers. So then it's just number of branches that you can have. If you're talking about resistance of any wire, which is between any two terminals. If you're thinking about the tension of your spring when you're connecting any two devices in dynamic system. If you're thinking about any tension which you are just having between a pair of atoms or molecule, okay? So those are all really interesting problem for the application of the graph, especially for weighted graph, which those lines have a weight, okay? Those lines or edges have a weight. And as I said, another one is distance highway between the pair of the cities. Those are really good examples. So your goal in this course is, I will say at the end, after learning all of those terminologies, is minimizing the weight. So you want to choose the path always to minimize the weight, okay? So in weighted graph is exactly the same, what we call vertices and edges. Go ahead.
So you said about you want to let the least amount of weight. Does that include every vertex, or like does that have to be a cycle at the end, or just?
That's a really good question. I have two specific name for them. If I take about Euler paths, I'm looking for each vertices. If I'm thinking about Hamiltonian one, I'm looking any edges, to travel any edges, okay? So it's coming soon. So it's either or both. So it's either both. So that's the type of problem we want to practice, yes. Okay. So remember, they are still simple graphs. They are still simple graphs. So which means no self loop, no multiple edges, and no, what was the other one? The directed graph. So these are still simple. The only thing is corresponding by any edge, you have a real number. So corresponding by any edge, you have a real number. As an example, from A to 5, the weight is 5. From D to C, the weight is -3, okay? And then another bunch of terminologies. So we have a little bit, again, terminologies, but I need to list them next time when we have the recap or review. I'll list all of these terminologies. As of now, we have learned five types of the graphs, and we have only vertex and edge. So we are adding more names. So first thing is the walk. What's the walk? Is really walking from one vertex to the other vertex. No condition. It could have repeated vertices, or it could be like Euler, as I said, no repeated. Okay, so that's just really in general. Walk is the one that you travel from one vertex to another vertex without any condition. So it doesn't have to be consecutive too. So you don't have to go from first one to the second one. You can go back and just forward as long as you go all of the vertices. That's just the walk. The other one, which we call it closed walk. So the other one that we call it closed walk is a sequence of the vertices, and then you start with the first one to the second one to the what was it? First one to the second one, and then you have the list of sequences. So if your first one is the same as the last one, that is called a closed walk. What's the difference between closed walk and cycle?
Like graph itself, or is a closed walk a path you're taking?
That's true. Cycle is the name of the graph, and closed walk is exactly sequence of edges. That's true. Okay, but it's really similar, right? So it is really similar. I can't ask you to give me a cycle. I must ask you to give me one closed walk on that graph, right? That makes sense. And then the other terminology is the length of your closed walk. What's the length of the closed walk? Is exactly the number of edges, huh? If you're just traveling k many edges, so it's just the number of edges. So this is coming one more time to compare right over here, exactly the same terminology, because just now, based on the problem, based on the what I defined over here, is just really saying what I ask you. A closed walk is said to be a cycle, which is not the same cycle that I just saw. That's another terminology. It's to be a cycle for any k bigger than 3, as long as you're traveling each vertex only one time. So one more time, what's the difference between closed walk and cycle as a path?
You can have a closed walk from V0 to V1, right?
So let's say you're having V1, starting from naught. So V0, V1, and then V2, and then V3, and then V4, huh? So I go from here, then go here, and then go here, and then go here, and then back. Okay? So that is, all of the vertices are different. All of the vertices are different. I don't back to the same one. So let's just go try one more time. So if I have a closed walk, is that okay if I go here and probably here, maybe go back on this one? Can I try one more and then go back on this one? And then go back on this one and then close it. So I'm going to write down what was my walk. I've started with the V sub naught, then V sub 1, and then V sub 2, and then V sub 3, and then V sub 0, and then V sub 4. For this one, I started with the V sub 0, and then V sub 1, and then V sub 2, and then V sub 3, and then V sub 4. Okay. Notation wise, actually that's a correct notation, but again, it depends on the book to the other book. If you use the comma is perfect. If you use these arrows also is perfect to show a path. Okay. This first one is a cycle. The second one is not a cycle because I have a repeated vertex. I have a repeated vertex. It's just a closed walk. Does it make sense?
So if it's repeated, it has to be the closed walk, and if it's not repeated, then it has to be the cycle, or can not repeated, closed and cycle.
Cycle says your vertices must not just repeat it. Everything has to be only one time pass, and then that's the only one, right? Okay, so if you are asking if it's repeated, because a closed walk can be repeated or not. So let's say, can a cycle to be a closed walk, or can a closed walk to be a cycle? So just maybe answer your question. If you have a closed walk, can it be a cycle?
No, this is repeated.
Okay. If you have a closed walk,
And the cycle would be a closed walk can be either repeated or.
yeah.
Is this a square rectangle relationship where all cycles are closed walks, but not all closed walks are cycles? Is that correct? I'm gonna figure that out.
One more time.
So all
Cycle.
squares are rectangles, but not all rectangles are squares. Are all cycles closed walks, but not all closed walks necessarily cycles?
That's true.
Okay.
That's true. That's true.
So let's say V4, there's no edge between any two vertices. They'd be neither closed one or cycle. If none of them went to V4.
If you mean I stop here,
Yeah, if you erase the edge between V0 and V4.
so let me just
Would
do.
that be a cycle?
If I erase here,
No, if you erase the edge between B0 and B4. And B3, B4.
one more.
B3 and B4. So that would be a cycle, but not a cycle. Since there's one vertex.
No, it's still a cycle. So no one says we have to just again. It depends on you have a cycle which is with the 4 vertices, 1, 2, 3, 4 vertices. It doesn't include the 5th one. It's fine. No, it still is a cycle. We don't have to travel every single cities, right? So if you just have a set of cities or just whichever object you have, right? No, that's still is a cycle.
So it doesn't have to include every verse?
No, not necessarily. No.
Or vertex?
No, not necessarily. Oh, no more time. Okay. So what do I have? Actually, for next class, for sure, I can finish the whole graph, but there are more examples is coming. Okay, so if you couldn't follow, there are really nice examples, nice application examples. Okay. Any comment, question for me? Did we have a quiz today or is on Wednesday?
It was from like last week.